Welcome back to The Explainer. I am honestly so incredibly excited to walk you through today's topic, mainly because it literally reads like a Hollywood thriller, except, well, it actually happened right under our noses. On May 14th, 2026, the open source community woke up to what I can really only describe as a high-stakes digital heist. But here's the crazy part. The attackers didn't smash their way in, they didn't phish anyone's passwords, they didn't steal static tokens. Instead, they pulled off this brilliantly terrifying supply chain attack that researchers dubbed the mini Shy Haul. What makes this absolutely fascinating is that they completely bypassed NPM's most trusted publishing features. We're talking about the exact systems built and recommended for nearly 2 years specifically to prevent these exact kinds of attacks. So we are going to unpack exactly how this went down, step by step. Okay, look at that number. 50 million. I really want that to sink in for a second. In a window of just 6 minutes, which, in the realm of automated software publishing is kind of an eternity, over 100 packages were compromised. And these weren't some obscure, forgotten libraries on the back shelf of the internet. These were massive packages that collectively see over 50 million downloads every single week. 50 million! And they did this without a single password being leaked, without a single developer getting tricked. The registry was entirely hijacked. So how on earth does an attacker pull off a heist of this unbelievable magnitude in just 6 minutes?
Part 1, the NPM nightmare begins.
All right, so let's dive into this. To really understand it, we have to start at ground zero with a massive, highly trusted project called TanStack. Now, if you work in the React ecosystem, you already know TanStack. It's huge, it's trusted, and it has a really sophisticated release pipeline. Well, the attacker knew exactly what they were looking for, and they targeted the automated heart of this project. The mechanics they used here are just wildly clever. See, the attacker didn't actually need to get a piece of malicious code approved by a human maintainer. Nope. Instead, they simply forked the TanStack repository. Then they created a pull request and literally immediately closed it. Poof. Gone. No one even had time to see it. But just the mere act of creating that pull request was enough to silently trigger a GitHub Actions workflow in the background. They essentially weaponized the CI/CD pipeline against the maintainers without a single pair of human eyes catching on. Now, you might be wondering how that actually works. The specific configuration flaw that made this all possible is called pull request target. When the TanStack team set up their workflow triggers, they used this specific option. What this means in plain English is that any incoming pull request, even a closed one from a random fork, was granted the ability to run in the context of the main repository. It inherited all of those lofty, high-level permissions from the main repo. And because of this single, seemingly harmless configuration choice, the attacker's code was authorized to quietly write a poisoned file directly into the shared cache of the CI server. The trap was set, perfectly hidden, right there in the infrastructure used to reuse dependencies between jobs.
And this right here is the climax of our digital heist. So this poisoned file is just sitting there patiently in the cache. Normally, an NPM publish token lives for just a few minutes in the CI's cache before going stale. That ephemeral nature is exactly why traditional phishing attacks usually fail. But as we know, this wasn't a traditional attack. A few hours later, a completely unrelated, totally legitimate pull request was merged into the main branch by a real developer. This totally innocent action triggered the workflow, which hit the shared cache, activated that poisoned file we talked about, and essentially intercepted the freshly minted NPM publish token right as it was generated. Boom. They grabbed the keys to the kingdom before the token could even expire. So, what was the immediate blast radius? 84. The exact moment the attacker intercepted that published token, they used it to drop the mini Shy Halud worm into 84 brand new, highly trusted TanStack packages. Instantly, thousands of developers relying on this ecosystem were right in the crosshairs. But of course, the attacker wasn't just satisfied with infecting one project. Not even close.
Part 2. The contagion spreads fast. This is where a localized vulnerability within TanStack rapidly transformed into a terrifying everybody problem. This worm was designed not just to sit there, but to actively hunt and propagate, and the speed of this contagion was absolutely staggering. Like, if you ran an NPM install on just one of those 84 poisoned packages, the malware instantly woke up and scanned your entire system. It was searching for anything valuable, sure, but specifically, it was looking for your own NPM publishing tokens. If it found them, it used your tokens to publish poisoned versions of your packages. Within just hours, major tech players like Mistral AI, UiPath, OpenSearch, Guardrails AI, and Squawk were compromised, pushing poisoned packages straight to the registry. The worm even jumped the shark from JavaScript over to Python, via compromised Python SDKs. It's crazy. By the very next morning, the security firm Aikido was already tracking 373 completely unique poisoned versions across 169 different packages. It was literally an exponential explosion.
Part 3, the persistence and the payload.
Okay, so it spreads like wildfire. But what exactly is it doing once it gets into a developer's machine? Well, this wasn't just a quick smash and grab. The attacker was weaponizing the very developer tools we trust and use every single day to make sure we couldn't easily rip the malware out. The really crucial point here is how this worm achieved persistence. It was hiding in plain sight. First, it started forging commits and signing them with the Claude Code GitHub app. By doing this, its malicious activity perfectly blended into the massive sea of AI-generated commits that maintainers are already so used to seeing. It was essentially wearing an AI disguise. Even worse, on infected machines, it embedded itself directly into developer environments like Claude Code and VS Code, meaning even if a vigilant developer realized what was happening and carefully uninstalled the bad NPM packages, the worm would just stubbornly re-execute itself the very next time they opened their code editor. It was practically glued to the workspace.
But honestly, perhaps the most ruthless part of this entire mechanism is the payload itself. The malware installed a literal dead man switch. A background process quietly ran on the infected machine, checking the validity of your stolen GitHub token every 60 seconds. The exact moment you tried to secure your account and that token expired, the malware activated what can only be described as war crime mode. It would instantly nuke your root directory, just completely erase your hard drive. If you try to clean it up, it destroys your machine. It's an absolutely brutal, zero-tolerance defense mechanism by the worm. Part 4. Protecting your codebase. So, we've seen the horror story, right? The inevitable question is, how do we actually protect our own code bases from this? How do you prevent a highly sophisticated attack like this on your standard everyday setups? Well, while we might not be able to prevent the initial registry breaches, there are some highly effective strategies you can implement on your local machine right now to drastically improve your odds. And this brilliantly illustrates a core difference in how we handle package management. So, a standard NPM setup installs packages immediately and implicitly trusts and runs install scripts by default. That right there is the gateway this worm exploited. But if you look at PNPM version 1 or higher, it fundamentally flips the security model. It blocks those automatic scripts by default and severely restricts dependencies from unknown sources. Let's actually break down exactly what that means for you. There are 3 specific lifesavers built into PNPM that effectively close the smuggling routes the Shai-Hulud worm relied on. First up, minimum release age. This brilliantly tells your package manager to absolutely refuse any package published less than 24 hours ago. And honestly, by the time 24 hours have passed, most malicious packages like this worm are already detected and pulled from the registry anyway. Second, block exotic subdependencies. Normally, malware can point a dependency to a random attacker-controlled S3 bucket or just some sketchy Git repo. This feature flat out refuses to install anything that doesn't come directly through a proper verified registry. And third, approved builds. Because most NPM malware does its damage through scripts that run the second you type install. This feature blocks all of them by default. It forces you to explicitly whitelist only the specific packages you actually trust to execute code. Using just these 3 defaults would have stopped this exact worm cold for the vast majority of developers.
Part 5. Healing production with Sentry. But hey, let's be real for a second. Even with the absolute best package managers and the tightest security protocols, complex distributed systems break, dependencies fail, and production issues are just inevitable. So when that jump scare Slack notification hits, how do we heal our production environments without manually tearing through logs for hours on end? The source material highlights a fascinating new approach using AI, specifically pointing to tools like Sentry's Seer Agent, which is currently in open beta. Instead of you panic scrolling through dashboards, this AI acts as self-healing software. First, it autonomously pulls all the relevant traces, spans, and logs based on the error context. Second, it intelligently walks upstream across your various microservices to locate the actual root cause of the failure. And third, and this is the crazy part, it doesn't just point out the problem, it actually drafts a code fix and opens a pull request for you to review. It is an incredible shift from reactive firefighting to proactive, AI-assisted healing. So, we've unpacked the anatomy of a perfect supply chain heist. We've looked at the terrifying speed of its contagion and the rigorous steps required to actually secure your local environment. It fundamentally challenges everything we thought we knew about relying on open source registries, which leaves us with one deeply provocative thought to close on today. Given everything we've seen, in a world where a closed pull request can silently weaponize a trusted pipeline, is a simple standard NPM install ever truly safe again? I'll let you ponder that one. Thank you so much for joining me on this explainer, and please, keep your repositories secure.